our team is ZoomSat. We have members from Harvard, UCLA, Stanford, and Cal Poly Pomona working on this project here, including Anthony Masias, Keshav, Luke, Matthew, Michael, Noah, and me, Victor. Next slide. So we're going to start with a mission statement for ZoomSat. The motivation behind ZoomSat was the fact that a lot of us live in California, and California has one thing that it's well known for, which is forest fires of all things. So we were thinking about that problem, and we were wondering, like, is there a method to try to sense forest fires and predict when they might occur, so that we can take measures to, prepare for those forest fires? We found a technology that is actually pretty relevant to this, and several missions that have tried to carry out, which is measuring evapotranspiration in plants. So evapotranspiration refers to how much water plants are evaporating, and that turns out to be correlated with fire risk, forest fire risk specifically. So there are very few current space missions that actually monitor and focus on this problem, and we think that there is a need for such detection to prepare for the increasing number of forest fires that California and frankly the United States is having. So our goal is to launch ZoomSat into low Earth orbit to collect evapotranspiration data and predict forest fire risk in California and the United States. Next slide.
So here's our proposed orbit. It is a circular polar orbit, and here's a quick simulation of what that orbit would look like. Its altitude is 500 kilometers with an inclination of 95 degrees and RAN of negative 64 degrees. So a few considerations that went into choosing this orbit are it's an accessible orbit, so it's a very common CubeSat orbit, so we can get into orbit easily. It's a good orbit track, so we would be able to cover a lot of the United States, and our initial goal was to cover California. And we'll talk about an example of one of our areas that we wanted to cover later, and good communication with our ground stations, which we had chosen as UCLA on the West Coast and Harvard on the East Coast. And here's a quick access from the Los Angeles ground station with the CubeSat over a 1 month time period. Next slide. So here's coverage of the United States over a month, which was my selected time period, and the percent covered with granularity of 1 degree in latitude and longitude is about 87.5%, and this is the area covered in kilometers squared. So we covered a good portion of the United States for anybody who would want to avail of our resources, and this can obviously be tweaked by changing the orbit, but this is the orbit that we went with for this mission.
So this first slide here is just discussing how we would first deploy the CubeSat. So for the CubeSat, we would be probably on a ride share with a rocket. Following some of the resources that we found online, following sort of how previous CubeSat missions have conducted their deployment, we were looking at, separating from the launch vehicle, whether that is off the ISS or off the launch vehicle, or just however that's done, waiting 30 minutes for the CubeSats to separate out, and then activating various sensors. So first activating the health beacon that I think is mandated on all CubeSats, and hopefully if there are amateur radio specialists available, trying to pick up a telemetry ping. Then turning on ADCS to do detumbling, waiting a while for that to stabilize, and then going into like an uplink listening mode. So at that point, once ADCS is stabilized, we would want to try to, once ADCS is stabilized and we start having our solar panels deployed, we would just start listening in for uplink. This is a pretty low power operation where it's just listening for a ground station to communicate to it. Once we establish contact, we'd start running through checkout, taking telemetry, taking sample images, checking and monitoring the health of different systems over time. And after a week of checkout, we would be free to enter proper mission operations.
Yeah, so once we enter the mission operations, Well, there are several different operational modes that the satellite can be in. So one of them is idle, which it'll spend most of its time in when it's not directly imaging or connecting with a ground station. And during this time, it'll be important to point our solar panels toward the sun so that we can charge our batteries. And then like Victor mentioned, we're gonna continue the health beacon every 30 seconds. And then we also will have a safe mode. So if we run into any issues like losing communication with certain components or we're reaching some extreme temperatures, then the system should be able to shift into a low operations mode, and then operators on the ground could try to assess the situation and see if they can resolve it. Next slide. And then a very important mode is the sensing mode, which is when images are taken of the ground. So we would specifically collect thermal infrared data from a target location. And this location would be a set of coordinates that are sent up as commands from the ground. So we would have the ADAC system help point the camera toward the target, and as we pass by, an image would be taken. And then stored in the OBC for downlink. Every time a status log would also be created just to make sure that the ground operators know if something went wrong. Another important part is calibration. So before each image pass, we would aim to take an image of a large body of water because their infrared emissivity and surface temperature is very well known or easy to find. So it'd be a great way for the ground operators to calibrate what they're seeing. So like mentioned before, we're running under the assumption that the Harvard and UCLA ground stations would be available for us. And there's also the possibility of working together with other members of the Blue Dawn Consortium if their ground stations would be available. But we would assume, first of all, that we can establish solid signal strength at a minimum elevation about 20 degrees when the satellite passes overhead of a ground station. And based on our payload, we found that an image size would be about 537 kilobytes, and roughly that translates to taking about 7.5 minutes of time to actually downlink one image. But what this basically means is that it's going to take multiple passes for one image to actually be able to fully transmit. And so that will be taken into account in terms of our scheduling. And we will also have time for uplink when the satellite is in access with a ground station for any updated coordinates, commands, or requesting specific files or troubleshooting errors.
So one of our primary goals was to look at forests and image forests. So a quick example that I simulated is the redwood forest, which is on the left picture what the red arrow is pointing to. That yellow highlighted region. So based on the imaging capabilities we're interested in, this would, as the movie shows, we will have one image be taken of our intended target area, which is highlighted by yellow. And while approaching California for this pass, we would first calibrate our payload over the ocean. So if we had if we look at the orbit of our Cubesat before and after our imaging, we will be directly over the ocean, so we will have time to calibrate our images before and after we take the image of the redwood forest. So next slide, please. So this process would take approximately, our pass over the area is approximately 20 seconds. But after that, we have these communication times over the next few days to communicate with and downlink data and telemetry after the pass to the ground stations in both Cambridge and Los Angeles. So as Noah mentioned before, it takes about 7.5 minutes per picture, which including 2 calibration pictures and 1 picture of the area in question itself, that would take approximately 25 minutes, or according to the durations of our access times, it would be approximately 6 passes. So our calibrating images, as I mentioned before, will be with large bodies of water, and which we will have access to before and after our area of interest in this specific example.
Okay, I'll be really quick here. This is just a brief sort of example of how maybe an image might be taken. So like, let's say we wanted to image the redwood forest, what would the process look like? And this is just sort of what we envision in terms of how we would run that image, right? We make a proposal for the imaging, we go through uplink, collect the imagery, and downlink, and eventually post-process that data later. Next slide. And this is just like a brief list of things that would go into that sort of proposal. Like, what do we need to think about when we take an image? Next slide.
Yeah, so this is our rough hardware and licensing budget. Our idea here was to maximize the amount of budget margin we had left for operation and testing. We found that with just the hardware that we included, we would average about $21,000 per unit in our 3-unit satellite concept.
Yeah, so really quickly, there's some basic licenses. There are probably more, but these were the most important ones that we found that we would need to acquire for the mission.
For the main payload that we will be carrying, we'll be carrying an infrared thermal imaging camera along with a 100mm germanium lens. And what we will do with this camera is that we will take thermal images of forested or agricultural regions across America. And as we listed in our mission objective, this can be used in a wide variety of industries, from forestry and wildlife preservation to determine fire risk, as well as being used in agricultural industries to determine irrigation and water plans to optimize crop yield. For some more specifics of what exactly the camera does, it has spectral response range here. And as you can see, we have our horizontal field of view of about 54 kilometers to 40 kilometers inside each picture that we can take. And this goes out really nicely. So we can take images of the redwood forest within a single image. So for more info of how exactly we calculate evapotranspiration rates, using the thermal data that we receive from our camera, we can calculate it using a SEBS algorithm as outlined in this article. And the thing that was cool was that they used this to determine irrigation rates in Iran in about 2016, 2017, using pre-processed data. But we think that we can use this data as well across America using our satellite images. And using the land surface temperature, as well as our calibrated data, we will be able to create maps of evapotranspiration. For the onboard computers that we decided to choose, we decided to basically use most of the GOM space economy because it has been flight proven and used in similar missions before us. And what's great about it is that it has a built-in software development platform already built in with it, which will make its development a lot speedier and integrate the parts well. And we don't need to create too many more extra PCBs to connect all the parts. For our flight software that we want to be using, we will be using the Nanomind built-in support package as our main interface with all the sensors. And then for overall usage, we can use NASA Core Flight System because it is open source and already made for us, which is really nice and really useful. And we can use some of the pre-made things as well as make our own mission-specific flight software. So using our data with the cameras, we can see that in a best case scenario, we have lots of storage left to take many pictures. And in case we do fail, we can see that we have maybe about 3 months worth of images that we can take before we run out of memory. and we should be fine because we will always remove images once we are done. So we should be good on memory budget.
So for the CubeSat size and mass, these are just some simple specs, but this is just a brief estimate of what we expect to have our CubeSat to weigh, roughly about 7 to 7.5 pounds. But again, this is just an estimate. It is just still a work in progress, so it's still subject to change. We calculated its center of mass in millimeters to its X, Y, and Z coordinates. Next slide. And we did a physical CAD render of what the CubeSat would look like. We still have a little bit of missing components listed in the budget, but it is still subject to change. And along with the models, like individual sizing and things like that. So again, this is still a work in progress, but this is just a rough estimate of what our CubeSat would look like on the inside. And if you can tell sorry, if you could go back, you could tell in the middle of the circle in the black and white, that would be the center of mass of the object. Next slide.
Okay, to talk about our ADCS system, we have 4 main control modes. We have a detumbling mode, attitude stabilization, thermal control, and sun sensing. Obviously, detumbling is to reduce the tumble of the ZoomSat, so we still have control of the angular rate. Attitude stabilization, so we are always facing the sun with our solar panels and facing the earth with our camera. Thermal control, just to move the thermal mass around to make sure that we can still remain in the operating range of our sensors. And then the sun sensing, obviously we have sun sensors within our solar panels. Just a basic outline of how our things are tending to work. As soon as we start going off course, we're going to have a signal to our magnetorquers, which are our actuators, to move the satellite back into proper orientation. And although we'd love to have the quick course as opposed to fine adjustment that reaction wheels would have, we're actually going with a flight tested magnetorquer rod. Specifically the NCTR M002. We're going to have 3 magnetorquers throughout the satellite for each axis for maneuverability. And then for the IMU, we're going to use the BMX 160 that has the accelerometer, gyroscope, and magnetometer all in one package, just to have an idea of what our acceleration, angular rate, and geomagnetic measurements will be. And then this is our sun sensor. Obviously, we're going to have these on all 6 faces of the ZoomSat so that we can properly get the power we need throughout the mission. These are our antennas.
Oh,
okay, you got it?
Sorry, yeah. It loaded slowly, but yeah, we're gonna use the UHF band. So this is the antenna we're using. It's nice because it's omnidirectional and it has nice impedance matching and polarization as well. And it hooks up really well to another GomSpace product, which is another flight-proven transceiver, and it also works extremely well with the OBC that we've selected and has been used in previous missions as well. And then these are very rough estimates of our link margins, and there's definitely a lot of room for error because we had to make several assumptions about our ground stations just based on a lack of available data or the fact that they haven't yet been like fully completed. So these are definitely subject to change and are very rough.
Our EPS system is based on sort of Clyde Space plus the EnduroSat solar panels, very flight proven, well used, and matches with all parameters. Here's a brief power budget. So you can see that on the left, the baseline draw power is around 2 watts. Seems to have a good battery life. We have enough battery to sustain downlinking for a while as well.
And just like with our presentation, we ran out of time to do thermal analysis, but we want to leave you with a quote from Will Smith saying, "Ah, that's hot," because our imaging camera only works from -40 degrees Celsius to 80 degrees Celsius, and we want to make sure that it's nice and warm and nice and cozy up there in space. Thank you for our presentation, and now we will open the floor to questions.
All right, thank you guys. Yeah, I think that's a good presentation. You did go over the time slot a bit, so I think we're just going to shorten the question section just to keep it within like a 30-minute total time slot. But yeah, if the judges have questions, go ahead and get started.
So yeah, you were mentioning the temperature range of the camera, and you said plus 80 degrees. Is that
-40 degrees Celsius to 80 degrees Celsius?
right? Okay, because it's an infrared sensor. Do you know which bandwidth you are looking at?
Yes, we are looking at bandwidth of about
Is
9. What?
Is it mid-infrared, far infrared, or low infrared?
I believe it is low infrared, but I need to double check.
Okay.
It said that we know that what it's capable of processing is, I think, 7 to 15 micrometers.
Is it flight proven?
Yes, it is athermalized and it has been used in flight before.
Okay, yeah, because those require huge heat sinks to make sure that they operate and they don't get a lot of thermal noise.
Yeah, we saw that inside of a previous mission before. They said that they found that it was a bit finicky, so they had to adjust something within the thermal analysis, which we did not get time to, but with given more time, we would look into that.
Good. Calibration. You mentioned that you would calibrate the sensor somehow. Did you guys put some thought into what target you're going to look at to calibrate?
Yeah, we essentially the calibration images would have to be large bodies of water, so oceans before and after taking land images. And the reason is because for taking thermal infrared data, it would be useful to have the IR emissivity of like a near black body, which water fits that model. So that'll just help the ground operators be able to calibrate and understand the land images. That was the basic concept we were going for, but we weren't able to look deep into the science behind like the calibration.
You usually point your camera also towards space to get basically just the background space radiation that is, nothing from Earth. And then of course, you need to correlate whatever measurements you make on the ground with, from space with measurements on the ground. Get water body temperatures and such from NOAA or somebody else, and that would do. Right. I have a very specific question regarding the structure. Why did you guys pick that type of aluminum?
So we picked it because it has good weldability when you're actually making the seals on the structure. It has good resistance to corrosion, especially in strong vibration environments. It has high fatigue strength with approximately of a PSI strength of 33,000. And it's a non-heat treatable material. So it's better at maintaining the strength as it through like cold working and hard straining of the material itself.
So you mentioned weldability. Are you planning on welding the thing shut so that it has an atmosphere inside, or are you just assuming that you'll put together the structure by welding it?
Like the actual methods of putting it together, it's still being looked into. But of course, we need to ionize the material first to prevent cold welding of the actual aluminum. So once we have that, we would probably pressurize the inside and then go from there, I would assume. But again, it still needs to be looked into.
Right. So is that because of you do need an atmosphere inside because you need some cooling or some sort of cooling for the camera, or because usually no CubeSat, I think, ever is has an atmosphere that is inside.
Seconded. CubeSats and pressure vessels do not mix at all.
Yeah. That's reason number one. So the point that I'm trying to make here is, and I'm asking about that because whichever thing that you choose has to have, let's say, a decision tree behind it. You can make your CubeSat out of steel, you can make it out of tungsten, you can make whatever thing you want, but it needs to have a good reasoning behind it. So atmosphere and such, not sure. Weldability, there are much easier ways to make a structure. But yeah, I mean, you did answer the question, so that's good. But just keep in mind that stuff like that, this is a very small detail in one of your slides, and I picked it up because it just popped up, and it's something that is not common. Michael, do you have questions?
In you're showing when you're imaging the redwood forest that the camera platform or the satellite platform was actually slewing, but I assume that this is just a nadir pointing sensor. If that's the case, do you have, which would then give you issues of getting the reference pictures before and after a actual shot, that if you can't turn it around and look at the sky or look out to space or look at a large body of water when you're doing the imaging, because you see that's pointing off to the side there. And I assume with magnetic torque, you're not going to get that type of accuracy to hold the satellite, so you can image you can dwell over a certain part or over a target there. Or did I miss something here?
I don't think we would be planning on slewing. It basically, like, this is just to demonstrate that there is a window open for us to take an image. We don't plan on slewing. And what we would possibly do is probably take, like, beforehand, take our calibration, use the magnetorquer to try to move it into a position where it can take the image, and then just time the image right so that it's over the redwood forest when we take the photo.
Yeah, so it doesn't have to slew. There are multiple windows even if the camera stays stationary, where we can take multiple pictures and still capture the redwood forest, but it will be over a larger period of time. And obviously, magnetorquers will assist in pointing it in an optimal angle to cover more area at one time.
And we found that the range the camera can be at an angle to take pictures was between around 4 degrees to 10 degrees. And when we were taking the shot of the redwood forest, it's at about 6 degrees. So we can always angle it a little off from there to take pictures of our black body for calibration as well afterwards.
Is there an optimal angle for imaging?
For our purposes, we wanted to make sure that our pixels would be well enough to see the differences between each forest. So we went for a pixel pitch of about 17 micrometers, which is about 85 meters per pixel. And we were able to achieve that, and we thought that was good enough. So we went with that number.
I mean, if you just kept your satellite and your sensor nadir pointing and stay in that attitude as you're doing the imaging, and then just as you overflew all the different areas, you'd ultimately cover all the landmass. Would that be a simpler approach, or would that, because you couldn't get the reference images, in the right times, or you'd have to collect so much information during, especially a pass across the, over all the land masses, right when you're in the middle of the land masses?
I think like nadir pointing is definitely the position we want to be in. We sort of, in this case, started off our project by focusing on specific locations to target.
Okay.
So like more forested areas. So for example, the reason why we picked the redwood forest as our initial target is because this is a pretty good initial target for us to start off with. It's in California, which has a motive for looking at this sort of research, and it's a nice big target for us to pick out. We probably want to prefer our camera nadir pointing, and like as the project develops, we could probably talk about trying to just continually scan over the entire US. But we do think that there are going to be specific targets that we want to point out that might not be exactly along like our direct downward pointing, and we would probably have to slew the satellite at least slightly towards the angle to get those photos. For example, our flight path doesn't exactly overfly the redwood forest, but if we point the satellite just a couple angles, just a couple of degrees off of the nadir, we can like hit the redwood forest perfectly.
What was the mission? I didn't see if I saw how long the mission would last, or how long do you think the satellite will, the lifetime?
We were sort of, I think KShop did the analysis based on a monthly, based on just the overflights in a month. We were probably thinking around a 1-year plan, similar to the lifetime of most Cubesat missions. This is, I think, something that would be most interesting in a couple month span, because then we can sort of see over the different seasons how evapotranspiration works. And there are different discussions about when this might be most optimal, like when it might be the most interesting, before a forest fire season or something like that. But that's for something that we did not think much about and we left for later in terms of mission planning, in terms of the details of mission planning.
So when it comes to the orbit, is there a reason why you guys didn't pick a sun-synchronous orbit as opposed to a polar orbit? Especially if you want to keep things, if you want to be able to compare data from previous days to data that you're taking, let's say, over the redwood forest. And in that case, why polar if you could, for example, use an ISS orbit, if you didn't care about day and night in that case, because those would be even more frequent when it comes to launch opportunities.
I think one of the considerations that we made was the altitude that we needed. So we needed a much lower altitude than many of the other orbits that we considered, and the polar orbit was at a suitable altitude for us for our specific camera. So I think that was the consideration that we chosen, that we made in choosing the polar orbit.
I see. So when it comes to the budget, I think you guys said 29K per CubeSat per unit. As far as I know, the Maryland ADCS module is already higher than that, right? When it comes to price, I think that module is actually pretty expensive. So I think the budget needs a little bit of tweaking in that case.
If I may add to that, the current budget as it stands is just a brief estimate. It is not the entirety of the amount. It is just a brief estimate as of the moment.
This is also a hardware budget, mostly on the parts of putting together a finalized CubeSat. This isn't accounting for development costs or like more expensive parts that we might need to swap in as the mission continues to develop. Right.
So the total budget right now it says 64K. But when you I see what you're saying. Okay. Per, let's say it's 21K per 1U CubeSat in there, I think. No.
Yeah, I think we basically, though, since the rules of the project changed to trying to account for cost per U, I think the 21K is a reflection of that. And again, our budget here is different from the previous team's budget. We didn't throw in lab costs or development costs as much. Yeah.
The 21 per U threw me off. I thought either I missed something about sending 3 satellites or something like that, or that you actually split it into each EU section of your CubeSat. But now it's clear. Okay. And just to keep it fair, I guess the same question. If I were to take some of your budget, where would you make the cuts?
I can try to answer that if the team doesn't want to. everything. I mean, I have my own thoughts, but I'm pretty sure the rest of the team might have a better thought on this.
Yeah, go ahead.
So I would say that there are certain parts of the hardware budget that we have here that are sort of for backup, and it would be very nasty to sacrifice backups, but it's doable. For example, the IMU is a backup ADCS part, considering that we have sun sensors, for example.
Okay.
I think one minor thing we didn't really consider was that there might be sun sensors already attached to the solar panels that we're getting, because we're actually getting the same models that the previous team had. So after hearing about that, it seems like the sun sensors are another redundancy that we don't need.
Thank you.
Okay. If there's maybe one more question to sneak in, then we can sneak that in. Otherwise, we do want to cut off the time slot. Michael, do you have one, or perhaps just any of the other attendees in general?
I guess
Can I
like
stop
really
a glance? Oh, sorry.
Just a really quick questions that like less about this satellite design itself, but how'd you choose the name ZoomSat?
If I may answer that. I think we chose it to be fitting because we're on a virtual platform at the moment. And yeah, I think the name was just fitting to the current situation.
All right. And okay, we'll squeeze in Da Cheng's question, and then we will cut it off. That'll be it.
Can I take a quick peek at your link budget?
Yes. Could you get that, Anthony?
The more expansive one in the
Yeah, you could just
spreadsheet,
open
or-
the spreadsheet probably.
Yeah.
Is that it?
You should scroll up. Yeah, so for this one, we had to adjust a lot of the values just based on the data sheet of the transceiver or the antenna that we're using. And then like basically a lot of assumption came in determining the values of the ground station, because we didn't really have access to any good information of the ground stations we were considering, or the ground station we're considering was not yet fully completed.
What's your antenna gain? It says 0.
For the spacecraft?
Yes.
Yeah, so I believe the max antenna gain was something like 1.6 decibels in the z-axis, but
because your
yeah,
antenna system is a bunch of okay. Yeah, that you should probably update that or find a different antenna.
And this is also in very rough estimates, we're saying again, and we tried getting in contact with UCLA's Elfin group, because they have built their own ground station over on campus, and they were unable to help us out in this time period. But if we had that data, we could have updated this a lot better.
Oh, I know. I've seen their ground station. I've worked on it.
Okay. Yeah, I mean the transceiver and antenna had a link budget in their data sheet, so we use a lot of the values from that.
Okay.
Yeah, that's kind of reflected in our link budget here.
1220 kilometers. Is that reflective of? I forget what your orbit looked like. Is that reflective of your peak length, or is that more of a middle length?
It's kind of like a worst case, actually.
Okay.
Yeah, that's the farthest length that we have between the ground station and Cubesat when we're trying to communicate.
Yeah, no, this mostly looks good.
All right. Okay. I am gonna shoehorn this this conversation onwards. So what we'll do is we'll actually break out into some breakout rooms. Flynn's be setting those up. So the judges, you guys are going to get 15 minutes to just talk amongst yourselves and deliberate. I believe the organizers, we're going to stay here in the main room, and each team is going to get their own room just to hang out in. And then we will return in about 15 minutes time to hear what the judges think overall.